Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating topic, brain-to-model transfer, essentially, training decision-making AI using the human brain as a teacher. It's a really exciting area that combines neuroscience with the potential to build more intelligent machines.
Yeah, I saw that paper making the rounds. The idea of using the brain as a blueprint for AI, it's something that's always been in the background, but it feels like we're actually starting to have the tools to do it in a meaningful way, you know?
It's definitely intriguing. But I also think we need to be careful. The brain is incredibly complex, and just mimicking its structure without really understanding why it works the way it does might lead us down a lot of dead ends. We can build complex neural networks, but are we really building intelligence?
That's a really good point. For me, I think the crucial aspect that's often overlooked is the spatiotemporal element. The brain doesn't just process information, it processes it in the context of space and time, and it's constantly translating between different coordinate representations. Current AI, even with deep learning, feels very brute force by comparison.
Absolutely. So let's break down this brain-to-model concept a bit. The basic idea is to record neural activity while a person is performing a specific decision-making task, and then use that data to train an AI model to perform the same task. The hope is that by mimicking the brain's activity, we can create AI that's more efficient, more robust, and maybe even more intelligent than what we can achieve with traditional methods.
Right? And the beauty of it is, if we can identify the key algorithms the brain's using for these tasks, we're not just building a system that performs the task, we're potentially uncovering fundamental principles of intelligence. Like maybe the brain is using a surprisingly simple algorithm for, say, risk assessment, and we've been overcomplicating it in our AI models all along.
I see the appeal, but I still worry about the black box problem. Even if we can train an AI to mimic the brain's performance, how do we know it's doing it for the right reasons? How do we know it's not just finding some spurious correlation in the data that won't generalize to new situations? I think neuro-symbolic approaches are important here, especially if we want explainable AI.
That's where the coordinate representation comes in. Because you can have a statistical model that's extremely accurate, but its coordinate system is arbitrary. It has no basis in the real world. To translate the brain's coordinate system over, you need to understand how it's representing space and time for a task and build that into your model. Otherwise, it's just another clever pattern recognizer.
Exactly. And there are different levels of abstraction in this too. You could try to directly model the activity of individual neurons, which is incredibly complex and computationally expensive. Or you could focus on higher level brain regions and try to capture the interactions between them. Different studies take different approaches, right?
Oh yeah, the level of detail is a huge factor. I think starting with simpler tasks and focusing on the broader network dynamics is probably the most promising approach initially. Like mapping out the flow of information between the prefrontal cortex and the amygdala during a decision involving uncertainty, that kind of thing. That kind of model could be translated.
But even then, how do you translate that network activity into something that's understandable and, more importantly, generalizable? We need to identify the underlying computational principles. What are the algorithms the brain is using to process that information? Just saying prefrontal cortex activates amygdala doesn't tell us anything about the underlying logic.
And it doesn't tell us how those activations are tied to a sense of space or time. The brain is making predictions about the future, it's remembering the past, and it's all happening in a spatial context. That's what's missing from a lot of these models.
Okay, so let's make this concrete. Imagine a study where participants are playing a simple gambling game and the researchers are recording their brain activity using fMRI. The goal is to train an AI to predict the participants' choices. Will they take the risk or play it safe? What are the key steps involved in a brain-to-model transfer in that scenario?
First, you'd have to pre-process the fMRI data, which is a whole challenge in itself. You're dealing with noisy signals and individual differences in brain anatomy. Then, you'd identify the brain regions that are most strongly correlated with the decision-making process. We are talking about the prefrontal cortex, anterior cingulate cortex, and insula likely being involved.
And that's where the interpretation comes in. You can't just throw the raw fMRI data into a neural network and expect it to learn something meaningful. You need to have some hypotheses about what those brain regions are actually doing. Are they encoding the expected value of the gamble? Are they representing the level of risk aversion? These things need to be explicitly represented.
And are they implicitly tying the gambling task to a location or a time? Is the subject thinking, last time I gambled, I was at the casino and I lost, or I always lose when I gamble on Tuesdays? These spatiotemporal associations might seem irrelevant, but they could be subtly influencing the decision-making process.
Okay, so say we've identified the relevant brain regions and we have some hypotheses about what they're encoding. The next step is to build a computational model that mimics those processes. That could be anything from a simple regression model to a complex neural network. The parameters of the model are then trained using the fMRI data, so the model learns to predict the participants' choices based on their brain activity.
And the key is to then test the model on new data, right? See if it can accurately predict the choices of participants it hasn't seen before. That's how you assess whether the model has actually captured something meaningful about the underlying decision-making process.
Exactly. And that's where I think neuro-symbolic approaches can really shine. Instead of just building a black box model that spits out predictions, you can try to build a model that explicitly represents the underlying rules and principles of the decision-making process. For example, you might represent the participants' risk preferences as a set of logical rules, and then use those rules to guide the AI's decision-making.
And you could represent those rules within a spatial or temporal framework. Maybe the risk aversion rule is stronger when the participant is in a particular environment or at a particular time of day. You need a way to integrate that contextual information into the model.
Okay, so what are some of the limitations of this Brain2 model approach? What are the challenges that researchers are currently grappling with?
The biggest limitation, in my opinion, is the quality of the data. fMRI data is noisy, it's indirect, and it has relatively poor temporal resolution. It's hard to know exactly what's happening in the brain at the moment a decision is being made. And EE data, while it has better temporal resolution, has poor spatial resolution.
Yeah, and there is the individual variability problem. Everyone's brain is wired slightly differently. What works for one person might not work for another. You need to find ways to normalize the data and account for these individual differences.
And there's the question of ecological validity. Most of these studies are conducted in artificial laboratory settings. How well do the results generalize to real-world situations, where the stakes are higher and the environment is more complex? Does the artificiality of the setting impact how spatial and temporal components of the brain respond?
That's a really good point, actually. Like, if you're studying risk assessment in a gambling game, that's very different from assessing risk when you're driving a car or investing money. The brain might be using different algorithms, or at least different parameters in those different situations.
And the interpretation of the data is always subjective. There's no single right way to analyze fMRI data or to build a computational model. Researchers bring their own biases and assumptions to the table, which can influence the results.
Okay, so despite these limitations, where do you see the most promising avenues for future research in this area? What are the key questions that need to be addressed?
I think one of the most promising directions is to combine Brain2 model transfer with other AI techniques, like reinforcement learning. You could use the brain data to initialize the AI model and then use reinforcement learning to fine-tune it and optimize its performance.
That's interesting. So you're using the brain as a starting point, but then allowing the AI to explore and discover its own solutions?
Exactly. It's like giving the AI a head start, but not limiting it to the brain's way of doing things. I believe a brain-initialized model has the best chance of finding a model that generalizes.
I think we need to focus on developing more sophisticated neuro-symbolic models. Models that can explicitly represent the underlying rules and principles of cognition, and that can reason about those rules in a flexible and adaptable way. We need to understand how the brain combines symbolic representations with sensory information to make decisions. How does the brain deal with noisy and incomplete information? And how does it learn new concepts and categories?
For me, it's all about the spatiotemporal component. We need to develop AI models that can represent and reason about space and time in a more sophisticated way. Models that can translate between different coordinate systems and that can integrate contextual information into their decision-making processes. I believe that requires going beyond current deep learning architectures.
So are we talking about spiking neural networks that more accurately mimic the temporal dynamics of neurons in the brain, combined with some sort of symbolic representation of spatial relationships?
Potentially. Or maybe it's something completely different. Maybe we need to invent a new kind of algorithm that's specifically designed to handle spatiotemporal reasoning. The key is to move beyond the limitations of current deep learning and explore alternative approaches that are more biologically plausible.
I think another important area is to develop better methods for collecting and analyzing brain data. Non-invasive techniques like fMRI and EEG have their limitations, but they're constantly improving. And there's also the potential to use more invasive techniques, like intracranial recordings, in patients who are undergoing surgery for other reasons.
That's an ethical minefield, of course. But if it's done responsibly and with proper consent, it could provide valuable insights into the workings of the human brain.
Absolutely, the ethical considerations are paramount, but the potential benefits are also enormous. If we can unlock the secrets of the brain, we could revolutionize artificial intelligence, create new treatments for neurological disorders, and gain a deeper understanding of ourselves.
And also, understanding how the brain integrates information across different modalities, vision, hearing, touch, is going to be crucial. Current AI systems often struggle with multimodal integration.
Yes, and how the brain uses those modalities to create a coherent, unified representation of the world.
That's a huge challenge, yeah, because it's not just about combining the raw sensory data. It's about understanding how those different modalities interact and influence each other.
And again, it's about the spatial and temporal relationships between those modalities. How does the brain integrate visual information with auditory information in a way that allows us to navigate our environment and interact with the world around us?
Okay, so looking forward, say 5 to 10 years, what kind of breakthroughs do you think we're likely to see in this area? What will Brain2 model transfer look like in the future?
I'm hoping we'll see more sophisticated neuro-symbolic models that can capture the nuances of human cognition and reasoning. Models that are not just accurate, but also explainable and interpretable.
I'm hoping we'll see AI systems that can reason about space and time in a more human-like way. Systems that can understand the relationships between different coordinate systems and that can use contextual information to make better decisions. That also goes for an understanding of the causal relations in the system.
I'm hoping we'll see Brain2 model transfer being used to develop new treatments for neurological disorders. Imagine being able to train an AI to mimic the brain activity of a healthy person and then use that AI to guide the recovery of someone who has suffered a stroke or traumatic brain injury.
That would be incredible. And I think we'll also see Brain2 model transfer being used to build more intelligent and adaptable robots. Robots that can learn from experience, that can adapt to new environments, and that can interact with humans in a more natural and intuitive way. It feels like the convergence of neuroscience and AI is really starting to accelerate, and the possibilities are endless.
I agree. It's an exciting time to be working in this field.
Absolutely. It's a challenging field, but it's also incredibly rewarding.
Definitely. And I think the more we understand about the brain, the better equipped we'll be to build truly intelligent machines.
Well, that's all the time we have for today. Thank you all for joining me for this fascinating discussion. And thank you to our listeners for tuning in to Cognitive Spirals. We'll be back next week with another exciting topic.